welcome. So, we are in Module 10 and lecture number 52 where we are discussing thermoelasticity or thermoelastic deformation. Especially we are discussing for uncoupled thermoelasticity. So, in the last lecture we have gone through the plane strain formulation. In that plane strain formulation, what we have done, we have just used the three-dimensional thermoelastic equation and especially the Duhamel-Newman constitutive relation that we have modified for the plane strain case, and in doing so we have also done for the displacement potential function, which is essentially u is del psi by del x and v is del psi by del y, and using this the two-dimensional governing differential equation is modified, and it turns out that after integration we could convert this to a single differential equation of that displacement potential function psi, which is a function of x y. So, for a plane strain case, this is this we have done in the last class, and in the solution of such differential equation is very general, which has been also taught to you in the engineering mathematics course or probably the higher mathematics course. In that the basic way of solving the differential equation is so you find out the homogeneous solution and you find out the particular solution, and then you add those two solutions to get the final solution of the differential equation. So, now in this lecture what we will do for the plane stress case. In that plane stress case, similar to the plane strain case, we will also modify it for the using displacement potential function, and then additionally we will also discuss the stress function approach, which you are already familiar with because we constructed the stress function earlier for the pure elastic deformation. In that for the pure elastic deformation, what we have seen is that the stress function exactly satisfies the governing equation. So, here also we will check that fact. So, to start with the plane stress deformation, which is a thin body, so that means the z direction it is very thin, so we can approximate as a two-dimensional body, and this plane stress case means there is no stress in z direction, and also the shear stresses sigma xz and sigma yz are 0. Similar to that the plane strain case, where the strain at the z direction is 0 and shear strain xz and yz is 0. So, in that case for the present case sigma zz and sigma xz and sigma yz is 0. Now, corresponding to this, we have also the non-zero strain components, which are epsilon xx, epsilon yy, epsilon xy, and then epsilon zz, because epsilon zz will not be 0 due to the Poisson's effect that we know from our earlier discussion. Now, to do this plane stress body under thermoelastic deformation, let us see what are the stress field finally we obtain. We obtain the stress field sigma xx, sigma yy, sigma xy, which are all function of xy, and all other three stress components are 0. Contrary to that, strain field is epsilon xx is essentially this part of the deformation is due to purely mechanical deformation that we know from our knowledge, and then the thermal part, which is alpha T minus T 0. And so, epsilon yy is also this thing is nu is the Poisson's ratio and 1 by E, and then the thermal part, thermal strain part. Now, here we are assuming the isotropic elastic body. So, there is one alpha, and alpha is constant in all direction. I mean the alpha is same for the all direction, that coefficient of thermal expansion of solid. Now, in case of an anisotropic body where you probably want to consider the alpha is different in different direction. So, these quantities may be alpha x, alpha y corresponding to that alpha x, alpha y and alpha z you can consider for the anisotropic body. But since we are mainly interested here the isotropic body where the alpha is actually constant. Now, here the epsilon zz will be there because of the Poisson's effect, and this Poisson's effect, this is how to derive this thing you have already known from your 3-dimensional stress strain relation, where probably you have calculated what will be the epsilon z. So, I just put the epsilon xx and epsilon yy in the 3-dimensional strain equation, and then finally we got this. Now, epsilon xy is again the shear modulus, and then shear strain, how shear stress and shear strain, how it is related. So, this is engineering shear strain. So, actually not gamma xy. So, epsilon xy, that tensorial quantity, and then epsilon yz will be 0 and epsilon xz will be 0, that we know from the earlier discussion. The only difference here is that you will have this alpha, the thermal part of the strain, which is additive with the usual mechanical component of the strain. Now, similar to the previous case, we will see the compatibility and the equilibrium equation. Now, in the equilibrium equation that remains same for a 2-dimensional body, we are considering here the body force is 0, because that will not generally affect the even if it is a constant body force. We have seen that compatibility equation does not change at all. So, but if the body force is a function of x and y, then obviously the compatibility equation will change, and that discussion has also been done in earlier. So, now once we get the stress differential equation in terms of, or the equilibrium equation in terms of stresses, we can substitute the previous expression for the stresses, and then we can put it the strain expressions. So, strain expressions, if we put the, which is a strain displacement relation, and then we get the differential equation in terms of strains, in terms of displacements u and v. So, which I have done it, and you can also try it there, and then this equation looks like this. So, it is two differential equation for two unknowns u and v, and then the important part is that this part of the differential equation is containing the partial derivative of temperature, that is T. T is a function of x y. So, that is the only difference. Now, again similar to the previous case, the compatibility equation, which is important. So, in the stress based formulation we need compatibility equation to satisfy and finally to calculate the displacements. So, here the compatibility equation is same, but once you substitute the strain components, which is discussed in the last slide, then you get the compatibility equation in this form. Now, if you remember that compatibility equation for the general plane stress case, which was del squared sigma xx plus sigma yy equals to 0, where there is a constant body force or no body force, constant body force or no body force. So, now this equation, only the modification is the thermal part of the thermal part of the deformation. So, this quantity is additive with the this quantity. So, this is for thermoelastic deformation. So, now you see this equation becomes a non-homogeneous equation, and this is a homogeneous equation. Now, if you also remember that in case of a plane strain deformation, we have also deduced it in the last lecture, which is in case of a E alpha, we had E alpha into 1 minus nu. So, this quantity for the plane strain condition is E alpha by 1 minus nu del square t. So, this is for plane strain condition. So, only difference with the plane strain and plane stress is this is actually E alpha for the plane stress, and plane strain is so this is del square t. So, plane strain is E alpha into 1 minus nu. Now, that is the only difference that we know. Even from the constitutive equation, the constitutive equation for two-dimensional plane stress and plane strain. So, that difference is popped up here in case of a thermal strain. Now, once we have this plane stress formulation, so we can now move to the displacement potential approach, which is essentially writing the displacement in terms of a single displacement potential function, which is your psi. So, psi is a function of similar to the earlier case, psi is a function of x y. So, psi I can write is a function of x y, and then this psi and this psi is how it is related with the displacement is del u del x and del psi del x, and v is del psi del y. Now, E1 and E2 are the unit vectors along u direction and v direction displacement, that is the x direction and y direction. So, now u vector is written in this form. So, this del psi means if I take the del operator or the nabla operator outside. So, now we know the equilibrium equation in terms of displacement from the previous slide. So, now I substitute this psi in the displacement potential in the governing equation. So, once I substitute that, I just need to rearrange it, and then after rearrangement I finally get this equation. So, this is for the u this first differential equation, which is of this form. So, now similar to that we will do the second differential equation. And this second differential equation again combining these two, we can integrate and then form a single differential equation compared to the previous case. Now, here let us do the second differential equation. So, in the second differential equation, similar to the previous one, I just substitute the displacement potential function, and then once we substitute the displacement potential function, it looks in the final form. So, this manipulation you can also do it on your own and then check that this is satisfied. Now, here once we get the two potential equation, that means one of them is partial of x with this quantity and one of them is partial of y this quantity, and this will be x for the previous case. Now, this is the two equations. So, in a final form. Now, once we integrate these two equations, we get again a Laplace Poisson's equation of this form. So, del square psi equals to 1 plus nu into alpha t. Now, this equation, if you remember, for the plane strain case, there was a difference here. For the plane strain case, what we have observed is that due to this difference in the constitutive matrix, we had del square psi. For the plane strain case, we had del square psi one plus nu by 1 minus nu into alpha t. So, this was for the plane strain case and this is for the plane stress case. So, the only difference lies in the this coefficient of this thermal part. So, other part is exactly remains same. So, this actually helps you to remember the equation itself. So, now, once we are done that, then the solution of this differential equation is similar to the earlier case, like we can just have two part of the equation, two part of the solution, which is the particular solution and the homogeneous solution. So, homogeneous solution we know how to do it, and then particular solution also we have to find out. So, this is the basic theory of solution of partial differential equation. So, now this after this actually we want to discuss the stress function approach, because stress function approach we have already seen. So, this stress function approach can also be applied to the thermoelastic deformation. So, here if you see that stress function that we have defined earlier, so this stress function can also be defined for where the non-zero body force is there. So, that also we have seen earlier. So, here the sigma xx is del square phi del y square, and sigma yy is del square phi del x square, sigma xy is minus del square phi del x del y. So, now if I substitute this in the differential equation or the governing equation of equilibrium, then it exactly satisfies. So, that property we have also earlier we have seen earlier. So, this stress function phi is known as the Airy stress function. So, now once we are equipped with the stress function, and this stress function is actually function of x y. So, phi is actually the function of x y. So, phi is defined as phi of x y. So, with this boundary condition also has to be satisfied, that also we have seen earlier. So, now once we know the stress function, then what will be the form of the final equation. So, the compatibility equation, again we know the compatibility equation from our previous discussion, that only this term, the thermal part, will be there. So, now I substitute the stress function, that is sigma xx and sigma yy. So, finally, it gives me another del squared. So, which is now this quantity becomes del to the power 4, that is biharmonic operator. So, we have seen that biharmonic operator equation in case of a purely elastic deformation, where this part only is 0. So, the biharmonic equation was for without the thermal deformation is del to the power 4 phi equals to 0. That was the for the purely elastic deformation. Now, except this, now this only the difference is here now is that the thermal part of the deformation. So, this is now is a non-homogeneous equation. So, this was a homogeneous equation. So, now this becomes a non-homogeneous equation. So, you will have the two part solution, again the particular solution, and then the homogeneous part of the solution. So, this two equation similar to the previous case, we can now solve this differential equation. So, essentially the stress function approach, if you look carefully, the compatibility equation plays an important role. So, compatibility, the reason already we have stated earlier, that again I am reiterating that when you need to satisfy the when you approach from the stress function approach or stress based formulation, or then finally you want to have the displacement solution. Now, displacement cannot be obtained unless you have the compatibility equation. Now, you have the from the stress, once you solve for the stress, you get from the by plugging the constitutive or the compliance relation, essentially you get the strains. Now, from that strains, actually you have to find out the displacements. Now, if you look carefully, that strains are, there are 6 number of independent strains, that is for 3D, and for 2D it is 3. So now from 3 in case of a 2D, 3 strains components, essentially you need to have a 2 displacement components. So that is a overdetermined system kind of thing, and this actually you need to so there will be non-uniqueness in the displacement. So for the uniqueness of u and v, you need the additional equation that needs to be plugged into, and that additional equation is compatibility equation. So this compatibility equation, along with the strain definition, you need to satisfy, and then finally you get the u and v, which is unique. Now, on the other case, where you actually formulate the displacement based formulation, that is, you start with the displacement itself, and then you calculate the you finally obtain u and v, and then you finally calculate the strains and stress finally. So in case of a thermoelastic deformation, the procedure is similar, very similar. The only thing is that the thermal strain part, which will act as a body force term in the differential equation, which we have seen here. So even in the biharmonic equation, this term will act as a body force term here. So this term is essentially the non-homogeneous part of the equation, and it has to be added with the governing differential equation. So in a nutshell, this is the procedure. Now, this kind of equation, solving this kind of equation, there are 2 approaches. One is analytical approach, another is numerical approach. Now, analytical approach can also be subdivided into semi-analytical approach and a purely analytical approach. So purely analytical approach is very restricted for the domain size and the distribution of temperature and all those things. And then semi-analytical approach, we relax some of we can alleviate some of these disadvantages, but again that is also very restricted. So finally it boils down that you enter into a numerical approach, and that is a universal approach, because you can solve for any geometry, any type of distribution of temperature, and any type of boundary condition. So all those things, a numerical approach is essentially useful for engineers like us, that we finally need some solution. So then this plane stress condition, actually this stress function approach can also be done for the plane strain condition, which you can appropriately modify. So this is for plane stress function approach. If you so if you remember my earlier discussion, this equation will have this 1 minus nu term here. So this term, the biharmonic equation remains same, only this factor is changed, which is divided by 1 minus nu. So similar to the previous case or plane stress case, again we will have this biharmonic equation will have 2 part of solution. One part is particular solution, another part is homogeneous solution, and sum of these 2 solutions is the actual final solution. So this is in a nutshell of plane stress and plane strain formulation for the thermoelastic deformation. So we will solve some of the problems and mostly the analytical, we will try to give the analytical solution, but I must mention here that the solution of such analytical problems are very limited, and if we get some analytical result, that's good, but unfortunately due to the complicated geometry, boundary condition, temperature profile, it is mostly impossible to find out a exact solution or the analytical solution of such differential equation. So, in such cases we follow basically numerical methods like finite element, like mesh free methods, finite difference methods, collocation methods, all other methods we follow. So, you must remember, studying these subjects or studying the objective of this material or the lectures is not just to throw you there that you finally try to solve an analytical equation, but essentially you need to know the differential equation, how it comes from. Then actually the numerical part by which you will finally able to solve this equation must be consistent with the theory. So, the theory part of these equations are very important in that sense, and also will show some of the analytical example by which you can solve this differential equation, and the solution is somewhat exact, but it is very difficult to get some results, as we have seen in case of a flexure, that equations are very big, and then the stress and strain components are very difficult to find out. So, we use principle of superposition and all those things to finally get the analytical solution. So, in brief, the objective of this module was actually to throw some light how the thermoelastic deformation happened, and how this deformation is actually creating the differential equation or the governing differential equation, which finally you need to solve, and what are the assumptions behind it, and how it is derived from the other theories. So, in the next class, so I stop here today. So, in the next class what we will discuss is, we will show some of the examples that we have, the theory for which we have studied in this 4 lecture, and basically we will solve some simple problems. For instance, strip problem and circular disc problem, those problems we will try to attack and get some analytical results. But again I am saying that objective is not to find out the solution analytically, because it has been proved, or it has been found out that finding out the analytical solution is very difficult for a general class of problems. So, I stop here. So, in the next class we will discuss some of the example for thermoelastic deformations. Thank you.